Hey guys, it's Mr. Sheeline here. This is going to be the video lecture notes covering 7.4 notes. Now we're finally getting to calorimetry. So just getting right to it. So what is calorimetry? Calorimetry is the study of heat flow and heat measurement within a particular reaction, within a particular system. And we're going to be using ideas such as heat capacity, which is, for the most part, just the same thing as specific heat. Heat capacity is the amount of heat needed to raise the temperature of a substance by 1 degree Celsius. Okay, so then it moves on to specific heat. Well, this is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So there's two different types of heat capacity. We look at specific heat using mass. There's another heat capacity you could also use, which focuses with moles, but we're not going to use that. We're just going to keep things nice and easy, nice and simple, and it's going to be for every 1 gram of our substance, we're trying to raise the temperature by 1 degree Celsius, and we got to know how much energy we need to put into the system in order to do that. So anyway, so calorimetry. How does heat go from one, I guess, in a reaction system, or how does it stay within the system? How much is lost? How much is gained? So we can actually do it, and these are the kind of problems you're going to see here. It's going to say like, well, the specific heat of water is 4.184 joules divided by 1 gram by 1 degree Celsius. Well, that sounds pretty spooky, but really all that means is this. It just means that it takes 4.81 or 4.184 joules worth of energy to raise 1 gram of water by 1 degree Celsius. Okay, that's all that means right there. That's all that means. So this right here are our units. Okay, those are our units for specific heat. Okay. And we'll kind of play with these, and I'm going to show you guys, just how you can double check to make sure that you're getting the right units. It's really just simple algebra, nothing too spooky. So here is our equation right here. So our equation for specific heat is Q divided by mass times the change in temperature. And we've got it laid out right here as to what everything is labeled as. So again, here we have C sub S as specific heat. We've seen that before. We're adding this crazy new item into here, this new variable. Heat is going to be measured in joules, which we know, but it's going to be labeled with Q. M, seen this before, this is for mass. And then delta T, which delta T is going to just be the change in temperature. Now, the way I'm going to be working through this, and the way that I encourage you, not only just encourage, but I almost basically want to force you guys to do, is the work I'm going to show you on these examples, because there's going to be a whole lot of numbers tossed at you, and we have to kind of take things slow, and we have to first figure out what we have and what we don't have. So this method I'm going to show you here is hopefully something you've seen before. If not, be prepared. It's not spooky. It's some tedious work, and this is the work I have my physics students, I have my physics students complete as well, because it is a great method to practice, and you will thank yourself in the future for basically building this skill, because it is a skill. Okay. So, and all it is we're going to label the variables that we have, the variable or variables that we don't have, and try to figure out what it is we have to do with everything. So let's take a look at this problem. So what is the specific heat of nickel if the temperature of a 32.2 gram sample of nickel is increased by 3.5 degrees Celsius when 50 joules of heat is added? Okay, so there's a whole lot of stuff going on in here, and it pretty much just looks like a problem that you would have gotten out of a, algebra 2 class or something. So, and it kind of is in a way, but more just algebra 1 really. But anyway, so let's break down what we have and don't have. So let's see. It looks like, what is the specific heat of nickel? So it looks like that we're trying to find the specific heat. of nickel. So what I'm going to do is I'm going to write C sub S equals question mark. I don't know what this is, and it looks like that's what I'm going to be solving for. Okay, and now, okay, so we're looking for the specific heat, and here's the condition. If the temperature of a 32.2 gram sample, so their sample of nickel, so that tells me that that's the mass of our substance here, and the temperature is increased by 3.5 degrees Celsius. So there's a change in our temperature, and the change is 3.5 degrees Celsius. When 50 joules of heat is added, it looks like we're adding 50 joules worth of heat. Okay, so I'm laying out all that I've got right here, making sure that I'm looking at the units, I'm reading the context of the problem to understand which one is which variable. Got my mass, I've got my change in temperature, I have my heat. And now all I have to do is just figure out how to put them in, so I'm going to rewrite my equation. So Q is over mass times delta T. There's my equation, so now I can just plug all that in. So Q, that's my 50 joules. I'm going to leave the units in here. Now, you don't have to leave the units in here for this kind of work. Arguably, you should, but I'm leaving them in this problem just to show you how we get the units that we should get, and just to double check. And then we've got mass. We got M there. We got mass, so 32.2 grams. And then I have my change in temperature. It's going to be times 3.5 degrees Celsius. Okay. All right. So, and then I'm going to solve for specific heat. So it's going to be, pop that into my calculator. That's going to be 50 divided by 32.2 times 3.5. And it looks like for my specific heat here, I'm going to get 0.44 joules over grams by degree Celsius. Now, if you notice, I'm switching the degree symbol back and forth on either side of Celsius, so don't be spooked about that. I'm much more in the habit of this. This is technically correct. This still works, so I should have it over here. Okay. So anyway, all right. So and this would be our answer here. So what does this say? So what does it say? Well, it says that the specific heat of nickel is 0.44, or that we have to add 0.44 joules to the system to raise 1 gram of nickel, or we have to raise the temperature of 1 gram of nickel by 1 degree Celsius. That's what we're saying here. Okay, and I know I get these units because looking over here at how I'm plotting in all of my units here, none of these units would cancel out, and so I'm left with whatever the number is, and then with J up top, joules up top, grams on the bottom, times the degrees Celsius on the bottom as well. Okay. Then also, last thing before moving on is going to be 0.44. So why 0.44? Well, that's keeping sig figs, because right here, that 50, 2 sig figs, 3.5, 2 sig figs. Mass is 3 sig figs, but remember, we're going to go with the lowest number of sig figs when we're multiplying and dividing. So here, in this case, it's 2, so our answer should also be 2. Okay. So this is just solving for specific heat. So when we solve for specific heat, this is what the work that I expect to see you guys provide. Okay. Now, this is not, I'm just going to say before, I guess one last thing before I move on. I'm going to say that this isn't necessary for the work to be this is not, I'm not going to include this as the work that needs to be shown. Really just this needs to be shown. However, this is, again, crazy important, and it's tedious, yes, but it lays out everything for you. It shows you what you have and what you don't have, and it's just great practice. Makes you just think a little bit more about the problem. Okay, anyway, so then heat transfer between reaction and the surrounding. So this is where we're going to be getting into basically calculating heat, because obviously heat is or I should say energy in the form of heat can be expelled. It can be absorbed. It just depends upon, what phase change we're going through. But heat energy cannot be created nor destroyed. So any heat lost by one substance needs to be gained by another. So in the case, like if we have heat of, if we drop some ammonium nitrate into some water, and it dissolves in the water, okay, there's going to be some heat that's released from the ammonium nitrate, and that's going to be the reaction, and then the surroundings will be the water, and we can calculate just how much heat was lost or gained, depending upon the temperature of the water. That's a very specific example. It's just to say that heat of the reaction is going to be equal to the negative heat of the surroundings. Okay, and it can be flipped around here too. It's also true that the negative heat of a reaction, basically meaning the loss of heat in a reaction, is going to be equal to the positive heat in the surroundings. Okay, there's energy expounded. So we can calculate heat with the same equation as the specific heat. We just have to rearrange everything, and here it is rearranged. Okay, all nice and neat for us. So Q now, still the heat, is equal to the mass times the specific heat of our substance times the change in the temperature within the reaction. So again, I'm going to go through the same methods I did before. So to just solve this, so we're trying to calculate the heat required to raise the temperature here. So all right, the specific heat of water is 4.184 joules divided by grams joules per 1 gram by 1 degree Celsius. How much heat is required to raise the temperature of 5 grams of water by 3 degrees Celsius? So, whole lot of things. We don't really know maybe we don't really understand what the question is. Let's just see what we have to work with. So, the specific heat of water. So, here it tells me we have specific heat, and we're just working with water. Okay. Let me get out of the habit, Ian. So here's our specific heat of water. Okay, well we have, what's the mass of our sample here? Well, the mass of our sample is 5 grams. And it looks like we want to change the temperature here by 3.0 degrees Celsius. Okay, well, and then it asks here, how much heat is required? What's the heat required here? Well, we don't know. So,
interruption, teachers. I am looking to borrow a small wet
sorry for the
this morning. I bought several of those
announcement.
If everyone can spare that today, that would be great. Thank you. Just let me know.
Sorry for the announcement there. So, all right. And then we have everything that we need, so let's just rewrite the equation. The heat is equal to the mass times the specific heat times the temperature. Okay. And we're looking for Q. We have everything that we need here to plug in, so we can just say Q is equal to the mass, 5.0, times the, and I'm going to write in the units to just show you how you can double check to make sure that the units are, like the units you get should be for, like that at the end you should get heat. The units left over should indicate heat. So then it's 4.184 joules divided by 1 gram by 1 degree Celsius times the change in temperature, which is positive 3 degrees. Okay. Then when you plug all that in, it should be 5 times 4.184 times 3, and you should get 62. You can't really see that. 62.76 is what you should get. Oh, I love the glare. 62.76. So what's my number of sig figs? Well, it looks like it's going to be 2, so it's just going to be 63. Okay, now what we're looking for heat. We know it's joules off the top of our head, but let's just make sure it's joules. So looking at all my units here, it looks like this is technically being divided here. So really, this is like, just to kind of write what this would actually look like, it would look like this. To kind of rewrite it up here, it'd be like 5 grams times 4.184, you can't see that, 4.184 joules times 3 degrees Celsius divided by 1 gram times 1 degrees Celsius. So this is technically what this line is showing. This is technically what it looks like. Okay, the units, grams, and Celsius at the bottom, just in these units, technically are being divided by the whole line here. So it would look like this. So this is how we know that this works out, is that because grams will cancel out, Celsius cancels out, and the only units we're left with are going to be joules. Okay. Again, we already know that because we're looking for heat, but just to double check, this is how we can double check up here. So make sure that, yeah, 100%, this is how we're going to calculate the heat within this particular reaction. And in this case, it's going to be 63 joules. Okay. So that's when we're trying to find the heat. Now, there's also going to be problems where, well, you've got the heat. This is all messed up now. Well, you've got the heat. Okay. You have the heat. You have the mass. You have the specific heat of a particular substance. But you need to find the temperature that it either started at or that it began with. So what this is like, this problem right here is like this example of finding temperature. Okay, this is like finding temperature right here. So, and that's what the change in temperature is. Change in temperature is saying that, well, we started at a particular temperature, we had an initial temperature, what we began with, well, and then we did a reaction, and then we saw that the temperature changed, and what it changed to was our final temperature. Well, it was the temperature we ended with. Okay, well, at least we ended when we stopped measuring at the end of our measurement. So, and the change in temperature is nothing but just the final temperature minus the initial temperature. Okay, so when we use this equation here in order to find either the final temperature or the initial temperature. Okay, so. And it says here you can also be asked to find either the initial or final temperature for a calorimetry problem. So just you can underline that too, just like, oh, this is what this problem is for. So again, we're going to use the heat equation here in order to find out what the either what the change in temperature is, or what the final temperature was, or is what the initial temperature definitely was. Okay, so let's take a look at a problem. So it says here that a 7.23 gram sample of water uses 774 joules of energy to raise the temperature of the water to 42.9 degrees Celsius. If the specific heat of water is 4.184 joules per 1 gram by 1 degree Celsius, what was the initial temperature of the water? So it's, excuse the interruption there, guys.
Now did receive a webcam. Thank you.
The question straight out asks us, well, what's the initial temperature? So we're looking for the initial temperature of water. So we're going to write big old T on the side, and it's going to be big T sub cursive, or like kind of squiggly I. Okay, that squiggly I is how I write my I when we're looking for like initial anything. This is just something that is super useful. It makes the I a bit more obvious that it's an I and not a J or not anything else. So T sub I, that is my initial temperature. Well, what else do we have? Well, it says here we've got the mass of our sample, which the mass of our sample is 7.23 grams of water, and it looks like uses 774 joules of energy, so that must be our heat energy. That's our Q. Okay, and to raise the temperature of the water to, so it looks like this would be after the reaction, or after just the experiment. So it looks like here our final temperature, T sub F, is going to be 42.9 degrees Celsius. And then, of course, the obvious specific heat of water, which you will get sick of looking at because it's going to be everywhere, 4.184 joules per 1 gram by 1 degree Celsius. Okay, so this is a whole lot of stuff. What do we do? So this is where we don't panic, and this is going to be a crucial thing to do here. Here we got to bust out our algebra skills, okay? So here is, we're going to rewrite the equation, and we're not going to plug anything in because we don't have the variable that we want to solve for ready to be solved for, because we have Q, we have M, we have this, but we need to figure out what that is. So what I want to do is I want to solve for this equation before we plug anything in. I want to arrange this in such a way that we have we're solving for initial temperature. So I'm first going to do this. I'm going to say, well, Q is equal to M times the specific heat times, and now I'm going to substitute in this little guy over here. I'm going to substitute in, because a change in temperature is just the final temperature minus the initial temperature. Okay, so I'm going to do that. Now what I'm going to do is I'm going to do some just simple algebra stuff. So now what I want to do is I want to get I'm trying to get these guys by themselves so that I can eventually use TI, initial temperature by itself. So what I'm going to do is that because M and C are being multiplied against these guys, I want to get them over here. So to do that, I have to divide on both sides. Okay. So then it cancels over here. And so then I'm going to now switch. I'm going to put these guys over here now. So final temperature minus initial temperature is equal to, and now I have this over here. I have Q divided by M times CS. Okay, so I have that. All right. Just noticing that if I put this here, the glare isn't so bad. Okay, so here's what I've got. Now I've got to get initial temperature all by itself. Well, it's a positive. We have a positive final temperature minus a positive initial temperature. So in order to get this guy out of here, I've got to subtract final temperature from both sides. So it cancels out over here, and it stays over here, and then I'm left with a negative initial temperature is equal to Q over M times CS, and it's going to be minus a final temperature. Now, we could solve here and then just at the very end switch it, but let's just keep things even simpler. Let's get rid of this negative symbol, and to get rid of that negative symbol, we're just going to multiply -1 onto both sides. Okay, so then that's going to get rid of the negative sign over here. This is going to then do this. I'm going to then have initial temperature is equal to, it's going to be now a negative, because this is now going to go here and it's going to go right here. It's going to be a negative Q over M times CS plus a positive now final temperature. Okay, so again, it's not hard, it's just some algebra. That's all it is. Take it step by step. And now you actually have the equation. Here's the equation. So use this every single time now. This guy right here, use this every single time you're asked to find initial temperature when you're given all of this stuff over here. Okay? Use this, please, for the love of God. So we have this set to initial temperature, so let's just plug everything in now and solve. So this is going to be Q, which up here is 774, divided by the mass, which is going to be 7.23, times our specific heat, which is 4.184, plus our final temperature, which is 42.9. Okay, let's just solve this guy real quick first. See what we get. Oh, that's a negative. And so let's see, we should get, so 774 divided by 7.2 times 4.184. So just keeping the sig figs in here, it's going to be negative 20, let's see, it's going to be just 2 sig figs. Let's see here, just to double check. No, not 2 sig figs, let's see. Hold up, wait a minute. Ah, I forgot the 2, 3. Shoot. Okay, let me try that again. 774 divided by 7.23 times 4.184. There we go. So keeping sig figs in this little guy right here, it looks like I'm going to get a negative 25.6. Okay, plus 42.9. Okay, so then I'm going to add those together. And here's what I will get. I will get a negative 25.6 plus 42.9. And what we get here is 17.3 degrees Celsius. Easy peasy lemon squeezy, man. So again, in the future, use this equation right here. Okay, I did the work for you. So if you need to solve for initial temperature, use this. And then here, let's actually branch off this. Let's branch off this guy real quick. Okay, just while we're still on this problem before we wrap up the notes. So I'm going to rewrite that. So this is in case you need to, and I would write this down, in the case that you need to solve for final temperature. So we've come back here, we've got the final temperature minus the initial temperature is equal to Q divided by M times specific heat, mass times specific heat. If we need to get this guy all by itself, it is literally just this. We're going to add initial temperature to both sides. That cancels out, gets rid of that, and here we have what we need. So here is the equation for solving for initial or for final temperature. Boom. Forgot to dot the I there. Here it is. So here is the equation to solve for final temperature. Here is the equation to use to find initial temperature. Use these same exact steps here if you say need to figure out the initial mass of your substance. I'm going to give you just these. I think we can put things together as good as we can if we need to find out what the mass is, because we can either use this equation or we could use we could easily use this equation here. We could use this equation here. It doesn't really matter. Okay, if we need to find mass, it's not hard, guys. So, but anyway, there is this last sheet on here. We're going to leave this guy blank. We're going to leave this blank for a bit. This is a decently more challenging problem. We'll see if we have time to get to that and to work on it. But we're just going to leave it blank for now. If you want to, there's plenty of room for you guys to give this a go, to try it out, maybe figure it out on your own. That's up to you. But anyway, this would be for calculating enthalpy changes. But we're not going to go over it again. But anyway, that's it for the notes here, guys. If you have any questions for me, let me know. If not, I'll see you in the next one.